you here on this wonderful Friday. We're now to the 16th lecture of this course. In the last lecture, we learned about band structure of solids, band theory. We realized that insulators are usually consisting of a filled band and then a gap to an empty band. A semiconductor is exactly the same, except it's a small gap, and a metal is when you have a partially filled band. Now, this band picture of solids is really useful because actually it gives you a way to understand a lot of the properties of solids, not just whether they insulate or conduct. And then what we're going to look at first today is optical properties. Optical properties. And just to remind you of things that you already know, visible light, you can see, ranges from about 400 nanometers to about 740 nanometers, corresponding to frequencies of about 3.1 eV to about 1.7 eV. So this is the red end over here, and this is the violet end over here. Now, when we talk about optical properties of a material, what we're actually asking is what colors are absorbed, transmitted, or reflected. So now let's think in terms of what we learned about band structure. Let's drop energy here. Maybe here's some conduction band. So this is empty. Then some valence band down here, which is maybe full. And there's some gap in between the conduction band and the valence band, E gap. Just to be definite about it, E gap equals minimum E of conduction band minus maximum E of valence band. Okay, so there's some gap, and we're going to send into this material a photon with some frequency h bar omega. Now, if h bar omega is less than the gap energy, h bar omega less than E gap, then the photon is not absorbed. Why is that? Well, in order to absorb a photon, what has to happen is an electron from the valence band is going to absorb that energy and get excited up to the conduction band. Empty. Empty. Has to get excited from the full conduction band up to the full valence band up to the empty conduction band. Now, given this, if you have a large gap, E gap, if E gap is greater than 3.1 eV, which is violet, then no visible light is absorbed, and what you have is a transparent material. All photons, I can't spell today, transparent material. All photons that are visible cannot get absorbed in the material because in order to get absorbed, they have to excite an electron to give up their energy. Okay? So the principle that we learned last time, that a full valence band is completely inert, holds true here, but the only exception is if you put in enough energy to excite the electron out of the full valence band and up to the empty conduction band, then that photon can be absorbed. So there are lots of examples of transparent materials that have large gaps like this, things like diamond, quartz, salt, glass. Now, glass is kind of special because it's amorphous. So it doesn't actually fit our picture of a, so what I drew here was a was k in that direction, and I was referring to crystal momentum. For glass, since it's amorphous, it's disordered, it's not a crystal, you can't talk about crystal momenta, you can't talk about reciprocal lattice, you can't talk about Brillouin zone, but nonetheless, the idea of having a full band and a gap and then an empty band still holds true for glass, and that's why glass is transparent. Now that may sound a little bit counterintuitive if you're thinking about the gaps as occurring from these periodic potentials opening up gaps at Brillouin zone boundaries, which is what we found in the nearly free electron model. But there's another way of thinking about where the gaps come from, which is from the tight binding limit, where you started with a bunch of atomic energy levels, and there's certainly gaps between those atomic energy levels, and when we bring them all together, bring all the atoms together to form a solid, electrons can hop from one atom to another, and the atomic energy levels spread out into bands, and you can still have perfectly good bands with gaps between them, even in an amorphous or disordered solid. Okay? So that's the physics that's going on in glass. Now, if you have a smaller gap, then only h bar omega greater than E gap is absorbed. So you'll have some colors absorbed and some colors just go right through. So let's show an example of this. So here's three materials with slightly different band gaps. The cinnabar, cinnabar, also known as vermilion for obvious reasons, has a gap of about 2 eV, realgar has a gap of about 2.4 eV, and sulfur has a gap of about 2.6 eV. For the cinnabar, if you look down here, where about the wavelength corresponding to 2.0 eV sits, at around 620 nanometers, only the wavelengths lower than 2.0 eV will go through without causing absorption of the photons. So it's transparent to the red colors, and it absorbs all of the higher frequency colors. So as a result, cinnabar looks rather red. Realgar looks a little more orange because it has a higher gap, and sulfur looks a little more yellow because it has a higher gap still. Now, if you look at sulfur, you'll see that 2.6 eV actually corresponds to a blue color, not a yellow color, and so sulfur is rather noticeably yellow here. But you have to realize that it's not just blue that's being transmitted through, it's all the colors to the left of blue that are being transmitted through. So you're seeing some sort of average of all the colors on the left of 2.6 eV, and that ends up looking yellow. So at least in some very crude picture, that tells you why it is that these different materials have appear different in their colors. And this picture of having the energy bands associated with the color of the material generally holds true. Now, there can be some complications with this simple picture. Actually, there can be a lot of complications to this simple picture. So let me draw another band diagram here. Let's imagine we have our conduction band that looks like this, and a valence band that looks like this. This is part of the Brillouin zone I'm drawing here. And you see that there are two different types of gaps we can have here. We can have this gap here, which is a straight up and down gap, two energies at the same value of k. This is known as a direct gap. Direct. And then you can have a gap from here to here, which is known as an indirect gap. And in this particular picture I've drawn, the indirect gap is a smaller energy than the direct gap. So it's just to give a definition that direct gap means delta K equals 0. It's going from the conduction band to the valence, from the valence band to the conduction band. So this is valence full, and this is conduction band, conduction empty. So direct gap means delta K equals 0, and indirect means delta K not equal to 0. Okay, so you can have these two different types of gaps in the material, and we should ask what kind of excitations can be made by light? Well, it takes only a little bit of thinking to realize that light mainly creates direct transitions. I'm not carrying chocolate today, otherwise I'd ask you why, but you know, I can't disappoint, so I'll tell you why. The reason is because for any given frequency, given that the speed of light is huge, k has to be very small. So if a photon is absorbed, it absorbs some amount of energy, but the electron that's excited can only absorb a tiny amount of momentum. So when a photon comes into a system, this kind of transition is made where the electron moves essentially vertically in this diagram, preserving its k. Now it doesn't exactly preserve its k, it can absorb a very small k, but the amount of k it absorbs is a tiny number because the speed of light is so large. And just to give you, sort of a point of reference here, the wavelength associated with light is thousands of angstroms long, whereas the size of the Brouillon zone, the k associated with the Brouillon zone is 1 over an angstrom, or 1 over the atomic spacing. So this number is an enormous k compared to the amount of k that a photon can give to an electron. So light mainly creates direct transitions, but not entirely. So light can weakly create indirect transitions. And there's several ways this can happen. One way is you have your light come in, and it creates electron excitation, indirect electron excitation, plus a phonon. And in this way, you can arrange this to work out by having the momentum associated with the indirect electron excitation equal the momentum of the phonon, but in the other direction. So an electron can increase its momentum this way, but the phonon will increase its momentum the other way, and total momentum will be conserved, even though you absorbed a photon. Okay? So this can happen, but it's very weak compared to the direct transition, which is a simpler process, which just simply excites the electron. So what one imagines is you have something like this, where you draw absorption on this axis, absorption of light, and h bar omega on this axis, and you have basically zero absorption. Then you get a little bit of absorption at the indirect gap. And then when you hit the direct gap, you get a huge amount of absorption. Direct gap. Okay? So that's sort of figuratively the how various materials with indirect and direct gaps absorb light. Now, the truth is a little bit, more complicated. There it is. So this is the absorption coefficient of silicon. Silicon has an indirect gap, which is lower energy than its direct gap. So here you see a little bit of a step. This is a log scale on the left, so what looks like a small step is actually an enormous step. But you see a definite feature at the direct gap here, where the absorption goes way up. And over here, there's a little bit of a feature at the indirect gap, where the absorption goes up, but not nearly as dramatically, much weaker. So it doesn't quite look like this idealized picture, but it's roughly, at least morally correct. Okay? All right, now, other materials that we've been studying include metals. And you know that metals are reflective. And this, I presume, you studied last year in your electromagnetism course, where you discovered that the reflectivity of an object has to do with its dielectric constant. And in fact, the dielectric constant really stems from the finite frequency conductivity of the material. So, the dielectric constant is a real and imaginary part, and you can calculate